A 1 kilogram rock is dropped from rest from a height of 80 meters. If air resistance is negligible, calculate the speed of the rock after 2 seconds. Since it's asking for something after a given time interval, we cannot use conservation of energy, so we're just going to use the basic kinematics that we've used in the past. So the initial velocity is 0, since it's dropped from rest. The acceleration is 10 meters per second squared. We're defining downward as the positive direction, since there's no upward motion here. And we want to know the speed after a time of 2 seconds. And we're looking for v. So just using the simple kinematics equation, v is equal to VO plus AT. No need to rearrange anything. When you plug the numbers in, you get 20 meters per second. Now in part 2, we're going to use conservation of energy to calculate the height of the rock after the 2 seconds. So at 2 seconds, we know the velocity is 20 meters per second directed downward. So let's use conservation of energy. E initial equals E final. The initial energy is when the rock is at the top, and the final energy, we're referring to the point after 2 seconds of free fall. So if we do K initial plus U initial equals K final plus U final. Let's look at which terms go to 0. The rock is dropped from rest, so the initial kinetic energy is 0. It does have height at that point, so it does have gravitational energy. After 2 seconds, it is moving. We just calculated its speed, so it does have kinetic energy, and it has not reached the ground yet, so it does have gravitational energy final. So we'll plug in the formulas. mgh initial equals 1/2 mv squared final plus mgh final. And you know the rest of this now. Cancel out the m's since there's an m in every term. Solve for the h final. And you should get an answer of 60 meters. Then calculate for part 3, use conservation of energy to get the speed of the rock just before it hits the ground. So we'll go back to the energy equation, EI equals EF, conservation of energy. This time, the initial energy is still referring to the top. The final energy is now referring to when the rock hits the ground. So with KI plus UI equals KF plus UF, the kinetic energy is still 0 because it's released from rest, but this time when it hits the ground, we're looking at right as it hits the ground, so it is moving, it does have kinetic energy. We're not talking about after it hits the ground and comes to a stop, we're talking about as it hits the ground. So it is moving as it hits the ground, but it doesn't have any height at that point because it has reached the ground. So the gravitational energy is 0. And then same as before, just set up the formulas. mgh initial is equal to 1/2 mv squared final. Cancel out the m's and solve for the v, and you should get a final speed of 40 meters per second. In part B of the problem, we are now going to introduce a non-conservative drag force due to the air resistance. So in part 1 of part B, we want to calculate the work done on the rock during the second half of the fall. So the work done by non-conservative forces, in this case the drag force, is equal to, now since the rock is moving downward, but the drag force is directed upward, the angle between them is 180, so we can just say it's the negative drag force times the distance the rock falls. The equation for drag force is B times V, and then times the distance the rock falls. We know that the B was given as 0.4. The V, the terminal velocity, was 25. And the distance the rock falls is at the halfway point. The total distance was 80, so the halfway point is 40. And when you multiply those numbers together, you'll get an answer of negative 400 joules. Now in part 2, so if that work done by the drag force is converted into thermal energy, we're going to use conservation of energy to show that the speed of the rock when it hits the ground is still 25 meters per second, which it should be since it had reached terminal velocity. So the way we want to do this is we're going to set up the conservation of energy equation, which is E initial plus the work that was done by the non-conservative drag force, which lowered that energy since that was a negative amount. We just got the negative 400. So adding a negative 400 to the initial energy means the final energy is going to be a little bit lower, since that mechanical energy was converted into thermal energy. So we can use the same thing we've been doing, but in this case, remember, we're looking at the second half of the fall. So the initial energy here is referring to the energy at the 40 meter height, and the final energy is referring to the energy when it reaches the ground. So if we set up the Ki plus Ui plus the WNC is equal to Kf plus Uf, if we figure out which terms go to 0, the kinetic energy initially, remember this is not from the very beginning when it was first dropped, this is from the halfway point. So at the halfway point, the rock was moving, so it does have kinetic energy. It also has not reached the ground yet, so it does have gravitational energy, so neither of these first two terms are 0. We already figured out the work due to the non-conservative drag force is negative 400. The final kinetic energy, this is the energy that it hits the ground with. It is moving as it hits the ground, so it does have final kinetic energy, but it does not have height as it hits the ground. So that's the one term that we can say goes to 0. So as we plug in the formulas, we'll get 1/2 mv squared initial plus mgh initial plus the work due to the non-conservative drag force is equal to 1/2 mv squared final. Does the m cancel out of this equation? We have an m in this term, an m in this term, an m in this term, but there's no m in this term. So we cannot cancel out the m, but we know every single thing in this equation except for that final velocity that we're looking for. So if you just rearrange this equation to get Vf by itself, basically multiply the whole thing by 2, so put all this stuff in parentheses, multiply by 2 to get rid of the 1/2, then divide it by m, and then square rootify that whole entire thing, that would give you the Vf. And if you add everything up perfectly, what you'll find, and it's easy to make a calculator mistake on here, but what you should find if everything is entered into the calculator correctly is that the final velocity is 25 meters per second, which is what we expected since that's the terminal velocity.